Welcome to Lecture 4 of Introduction to Computer Architecture. I'm Simon Moore, and today I'm going to tell you about reduced instruction set computers. So what is an instruction set architecture? Well, it is the repertoire of instructions or primitive operations that the processor can perform. There are many ISAs out there, although commercial reality has really reduced things to two very significant ones. The first one is the Intel or AMD x86-64 architecture, which is a complex instruction set computer style instruction set. I will talk a little bit about this in the last lecture, lecture 10. And then we have reduced instruction set computers, RISC. And a good example of this is the ARM processor, who have their headquarters in Cambridge, and they produce 32-bit and 64-bit processors used in mobile phones, Raspberry Pis, and many other devices. And then there are open source instruction set architectures, and the one that we're going to focus on is RISC-V, which originally came out of Berkeley in the US and is gaining quite a lot of attraction. It's now managed by the RISC-V Foundation. And we're using it in Cambridge for a number of projects, including Cherry RISC-V, which adds security improvements, and spin-outs like Low Risk, which produces open source silicon. There are other open ISAs out there, including old industry design, so OpenSpark. Spark came originally from Sun Microsystems, and MIPS Open. MIPS is another company that is largely, well, it's been sort of sold and acquired and respun out and various things, but it seems to be slowly dying at the moment. And then there are community-driven designs like OpenRISC. We're very much going to focus on RISC processors for the rest of this lecture, and RISC-V in particular. The key idea in RISC is to make the common case fast. So it's born out of a push for quantitative computer architecture. In other words, we measure the improvements and we only include the things that will be used regularly. This ties in with Amdahl's law that I talked about in a previous lecture. It also assumes that we're going to use compiled languages. Now, this seems obvious to us now, but actually back in the old RISC days, there was much more focus on giving the assembler writer a rich instruction set to program against and minimizing the semantic gap. And really what happened is when researchers at IBM principally started looking at how to build simpler processors for an application, they realized that they could also make them go faster and then use and make sure that basically the instruction set was a good target for a compiler rather than the instruction set being a good target for the assembler writer. Another key property of RISC instructions is that then it's normally what's called an orthogonal instruction set. And this really means that the operations are usually independent from which registers you use. This is actually in contrast to RISC, where there are often instructions that use specific registers. So, for example, there might be a register used specifically for loop indexing. So you'd use it in for loops. However, in RISC processors, generally speaking, all the registers are general purpose rather than being specialized. Although the compiler may choose to use certain registers in a particular way, for example, using a particular register as a stack pointer, but the processor is generally unaware of that. The other thing that's really important is that RISC instructions are usually simpler to decode. The instructions themselves, in their binary representation, are often just 32 bits long, perhaps with the option of a compressed 16-bit format for certain instructions. So that really helps. In contrast to RISC, I mean, in Intel you can have anything from a byte up to, I can't remember, about 16 bytes. We'll talk about that in a bit more detail, and it's very complex to decode. I'm now going to present some slides that were produced by a good friend of mine, Krista Osanovich, at UC Berkeley. And this is really if you like, a propaganda pitch for RISC-V. So Krista argues that instruction set architectures don't matter to some extent. You know, most of the performance and energy running software in a processor is due to, firstly, algorithms, application code, the compiler, the operating system and runtimes, then to some extent the instruction set, and as we work our way down the stack, we then get to microarchitecture, so how do you actually design the processor, and the memory design, and that's obviously critical for power efficiency, the actual low-level circuit design itself, the physical design, so layout of transistors and so on, the fabrication process, and in a complete system there are also really significant things like displays and radios and DC to DC converters and sensors and things. You know, if you think about a mobile phone, a lot of power is used by those. So in some sense the ISA doesn't matter. However, the ISA does matter in that it's the most important interface in the computer system. It is the interface between hardware and software. If you like, it's the contract that the hardware designers provide to software that you work against. There is a large cost to port and tune all the ISA dependent parts of a modern software stack. So that includes things like, you know, the compiler and the linker and debuggers and so on. There's also cost to recompile or port and do quality assurance on all supported ISAs, although obviously the compiler tries to take a lot of, you know, most of the time you try and write code that is not processor specific. If you're using a proprietary closed source, you may be using proprietary closed source code, and I'm afraid there are examples where people end up with, you know, binaries and they don't have the source code, so you can't recompile. You can also run into problems of bit rot, where you can no longer compile your own source code. So if you've got some source code that's been around for a while, it might be, for example, say the C standard has changed and your C code will no longer go through a modern compiler. You could have lost your source code, and most of the cost of developing a new chip is developing software for it. And most current large chips actually run multiple instruction sets. So if the choice of ISA doesn't have much impact on system energy or performance, and it costs a lot to use different ones, why isn't there a free open standard that everyone can use for everything? If we look in the open source software world and the standards world, then, you know, from networking, both the hardware and software, things like Ethernet are standardized, and then there are open source and proprietary stacks that work with those networking. You know, in the OS world, we've got standards like POSIX, and there's free operating systems like Linux and FreeBSD, and proprietary implementations like Microsoft Windows and so on. And on the compiler front, you know, the standardized languages like C, and there are open source compilers like GCC and LLVM, and also proprietary compilers. So the Intel compiler is super optimized for Intel. ARM have their own compiler, although I believe most of the time these days they use LLVM. And in databases, you know, we've got standard interfaces, you know, the SQL language, and there again there are free versions and proprietary versions. And also for graphics, you've got OpenGL, and then there are free and proprietary graphics libraries. But on the processor architecture side, there are no standards, and there's few free open implementations, and it's really those gaps that RISC-V is looking to fill. And there are certainly plenty of proprietary implementations like Intel AMD x86 machines and the ARM processor architecture. So if we've got successful and free open standards in the software world, why not for processors? So the sort of propaganda is the instruction set architecture should be free and open. ISAs are proprietary for historical business reasons. There's no good reason for the lack of free open ISAs. It's not an error of omission by ISA owners, nor because owners do most software development, nor are most popular ISAs wonderful ISAs, to be honest, nor are the companies great stewards of the instruction set architectures, nor can only owners verify the ISA compatibility. And it's not as if buying a proprietary ISA protects you from patent lawsuits either. And finally, proprietary ISAs are not guaranteed to last and may actually disappear. So to provide some background to RISC-V. In 2010, after many years of using MIPS and Spark, in Berkeley this is, and to some extent x86 as a basis of research, they decided that it was time to look at a clean open ISA for the next set of projects. The ISAs that were around were x86 and ARM, but x86 is really impossible. It's too complex and a lot of IP issues. x86 architecture has over 1,300 instructions. The manual's enormous. The instruction length varies from 1 to 15 bytes, so it's complex to decode. ARM is almost impossible. It's a little bit baroque, although ARM v8 is quite a lot cleaner, but there were a lot of IP issues. Fundamentally, ARM is an IP company. In ARM v7, so the older 32-bit instruction set, there are around 400 instructions, but the manual is still pretty large and complex. So they thought, well, we've seen lots of instruction sets. Why don't we just design a fairly simple, clean instruction set as a nice 3-month project? Well, it's taken them several years, actually, to really do this properly. And, after 4 years, they'd frozen the base user spec. And they'd started to see, some people in industry taping out chips. And there were certainly lots of research publications. Although a lot of the tape outs, I have to say, are being in devices where the person producing the chip controls both the hardware and the software. So a good example of this is Western Digital, who do hard disks. And what's critical there is if they find a minor bug in the hardware, then they can fix it up in their own software. And so that de-risks things. And standardization efforts continue to go on for the privilege mode and other bits of the instruction set on RISC-V. So what is RISC-V? Well, it's a new free and open ISA developed at UC Berkeley, as I said, now controlled by the RISC-V Foundation, and it's free, both in the sense of free as in beer and free as in speech, so you can do whatever you want with it. It's designed for research, education and commercial use. It's not just a free ISA. They also think it's a pretty good ISA. I would argue that it basically refines the whole idea of RISC instruction sets. It takes a lot of ideas from older ISAs like MIPS and cleans things up. So if you like, it's sort of consensus ISA. Because of the emphasis on simplicity, though, it's really useful from an education point of view. So what's different about RISC-V? It is simpler. It is nice and simple. It's far smaller than commercial ISAs. It's a clean slate design. Well, as I said, a lot of influences from MIPS, but it's pretty clean. There's clear separation between user and the privileged instruction set. I'll talk more about privileged instruction sets in a later lecture. It avoids a lot of microarchitecture or technology-dependent features which tended to happen in much earlier ISAs like MIPS. It's a modular ISA, so there's a small standard base instruction set, and then there are multiple extensions, and there are also sort of common groupings of extensions, like the base integer instructions and say multiply plus divide and floating point and a few other bits and pieces form a sort of general purpose processor. It's designed for extensibility and its specialization. So there is a variable length instruction encoding, but they make it very simple to decode nonetheless. And the base instruction set is 32 bits with a compressed instruction set at 16 bits, and then an option to go for slightly longer instructions. So there's a vast opcode space available for instruction set extensions. And it's stable. They're basically doing a sort of standardization effort, and the extensions are eventually frozen, and there are additions via optional extensions, not new versions, if you like, of the processor. In other words, if you've got a piece of code that's compiled for the base instruction set, it should run on any processor. So RISC-V is not an open source processor, it is an instruction set specification, an ISA specification. They want to encourage both open source and proprietary implementations based on that ISA. And most of the cost of hardware design is actually in software, so we want to make sure that that the software can be reused across multiple chip designs. And then expand to have open specifications for whole platforms, including I/O and accelerators. So the RISC-V base is the integer. RV32E is RISC-V 32-bit, and E is the 16-bit register subset of RV32I. Let's not worry about that one. Most people use RV32I, which is the 32-bit instruction set with 32 registers, or RV64I, and there is an option for a 128-bit processor, although that's not yet well defined, it's not standardized. And you need less than 50 basic instructions in the hardware for a basic system. And then there are standard extensions so there's the M extension, which is integer multiply and divide. There's atomic operations, single and double floating point. So in fact, I, M, A, F and D together form what they tend to refer to as the general purpose instruction set. And then you can add extensions on top of that, for example, quad precision floating point and various vector extensions and lots of other things. All of the above are fairly standard for a RISC processor, and the user level components were frozen back in 2014, and basically the idea is that those basic sort of general purpose stuff will be supported forever. We're going to talk a bit more about how you actually encode instructions. So there are basic encoding types, so how you pack the information into 32 bits of information. So quite a lot of instructions are what they call register to register, an R type, and that's the one on the top line. And then you can have other forms of instructions, so I type, S type and U type, where the fields change a bit. So for this base instruction set, it's 32-bit fixed width, what they call naturally aligned instructions. In other words, the instructions are on a 4-byte boundary, so there's no complication during instruction fetch for the processor. It just reads a 32-bit word in. And by the way, it's a 32-bit instruction regardless of whether it's a 32-bit processor or a 64-bit variant. There are 31 integer registers, registers 1 to 31, and there's also register 0x0, which is always 0. There are source registers called S1 and S2, and a destination register RD, and because there are 32 registers, that requires 5 bits, and those 5-bit fields are in fixed locations in the instruction set. So for instance, if you look at S-type, S-type instructions happen not to have a destination register because they're typically store instructions, and so those bits are then used for an immediate field. But you'll see that the source registers are always in the same place, and that makes the processor design more efficient. The immediate fields, these are the things marked IMM, are sign extended, and you have to do a certain amount of decoding on those. There's also, if you've got floating point, there's a separate set of floating point registers, and there's also what they call CSR registers that are specific to floating point, more later. And the instruction set is also designed to support position independent code and dynamic linking, which are just basically typical ways we want to compile code and link code today. More details later. So let's look at RISC-V registers and memory in a little bit more detail. As I said on the previous slide, RISC-V has 32 registers called X0 to X31, where X0 is always 0. The register file provides very low latency access and is multi-ported. In other words, you can read 2 or more values and write a value every clock cycle, depending on the complexity of the processor. It's got to be a minimum of 2 reads and a write to complete most instructions. Memory usage is conventional in that we have a linear address space for both instructions and data, and there's optional page-based virtual memory protection to simplify memory management, and also to provide some protection between application threads. Further details in a later lecture. Addressers are 32-bit for the RV32I base instruction set. There is, as I mentioned, an RV64I for 64-bit addressers, and there's a sort of prototype for RV128 for 128-bit addressers if you really need a lot of memory. They're all still based around a 32-bit instruction format with, the 16-bit compressed instructions and extended instructions possible. Let's look at some example instructions. If we want to just add 2 registers together, so we want to do the sequence x3 is x2 plus x1, then in assembler it simply add x3, x2, x1. If we want to add 1 to register x3, then the 1 is an immediate, and what I mean by that is the constant 1 is held as part of the instruction, and we use the add I, the add immediate mnemonic for the operation. Similarly, if we want to put a constant -5 into register x5, we would also use an add immediate. Here we've used x0 because that's the 0 register, so we're basically adding -5. That -5 is there again it's an immediate. It would be some number of bits that are then sign extended. If we want to load a word from memory at a particular location, then RISC-V just provides one very simple addressing mode, and the addressing mode is basically what address calculations you can do before you actually do the load operation. And here we've got a simple example of loading using x3 as the address, and we're adding 0 to it. And the format, which I always think looks slightly weird, but this is what's often done in assembler, is 0 brackets x3 means basically x3 plus 0. and the result from the load word LW goes into register X4. And also, if we look at, say, branch instructions, most jumps in RISC-V, as a lot of other instruction sets, are what they call relative. So in fact, the direction of the branch is specified as an offset from the program counter. We don't tend to write the offset directly in our assembler. We tend to use what are called labels, and you'll see that in a minute. In this particular example, we're doing BEQ of X4, X5. So what that does is it basically causes X4 and X5 to be compared. Typically, actually, the processor will just subtract them and check to see whether they're 0 or not. And if that condition is true, then basically the offset is added to the program counter, and that determines what the jump target address is. Let's look at assembler versus machine code. So we've got an example assembler instruction here, add I of x5, x0, -5. So this is the human readable form, and the assembler just converts that into binary machine code, which is a very simple process. Okay, this particular instruction is an I-type instruction, and the I-type format that we just look in the specification for the instruction set is as follows. So we have a 12-bit of immediate, so that encodes the constant into the instruction. We've got 5 bits for the other source register, so RS1, and in this case it's X0, so which will give us the value 0. And we just encode 0 in those 5 bits. The funct bits and the opcode bits, there again we just look them up. They're just defined in the ISA manual. So we look those up and we just fill them in as appropriately as part of the encoding. And then finally we've got RD, which is the destination register, and that's X5. And so we just put the integer 5 into those 5 bits in the RD field. And then in machine binary, I've written the binary representation at the bottom, and I've used underscores just as spacers. So it's just that binary, 32-bit binary number that ends up in memory. And obviously what the processor does is when it reads that 32-bit instruction out of memory, it then decodes all of those fields in order to figure out what instruction needs to be executed. Now let's look at calling subroutines. Standard way we do a subroutine call is what's called a jump and link instruction. So that's called JAL. We've got a destination register, RD, and we have an immediate, which is actually a slightly larger immediate than the I-type instructions. And what this actually does, it performs the following operation. Firstly, into the RD register, which is typically, used, it's basically going to be the return address. It stores the program counter +4. In other words, the program counter at which JAL was fetched +4, and that gives us the instruction after the JAL instruction. In other words, where to return to, having done the subroutine. And then the program counter is we then to the program counter add a sign extended immediate. And then there are pseudo instructions in assembler which are just conveniences. So for instance, there is a call instruction, and this is a pseudo instruction. It doesn't really exist in the machine code. The assembler actually replaces it by JAL RA immediate. Okay, so call immediate turns into a JAL RA immediate, where RA, as we'll see on the next slide, is the return address as defined in the calling convention ABI, and actually ends up being register X1. In order to return from a function, there is a ret pseudo instruction, and that actually there again gets replaced by a real machine code instruction. And here there is a JAL-R, which is basically a jump and link with a register specifying the place where you want to jump to. Okay, so it's a more general instruction than return. And so return gets expanded out into a JAL-R, where the destination register is register 0, x0. The register that specifies where we're going to is RA, the return address, and the immediate offset is 0. Okay, so basically all this does, it sets the program counter to be whatever value is in the RA register. Okay. Yeah. Let's look at the RISC-V calling convention. So this is what is used by the compiler and linker, and how sort of library calls are done as well. So whenever we do a subroutine call, by convention, this is how particular registers get used. Now you will remember that I said that generally a good principle in RISC-V or in a RISC instruction set in general is to keep the register's general purpose. So from the processor's perspective, it really just understands that x0 is always going to be 0. For the other registers, it just treats them all the same. So what we're looking at here is just a convention used by the compiler. So let's look at the first one. x1 is the return address, and that's just a convention. Okay. Similarly, x2 is usually used as the stack pointer, x3 is the global pointer, and x4 as the thread pointer. And then we put temporaries in T0 to T3, T0 to T2 are in registers x5 to x7, and so on and so forth. You'll notice there's a column marked caller, and this determines when a subroutine is performed, who has responsibility for saving any registers before they get overwritten. And this basically, if you think about it, if you call a subroutine, when you return from the subroutine, you don't normally expect your state to have got disrupted. Okay, so and there is a choice. If registers need to be used, who's going to save them? Either the caller or the callee, the routine that's been called. Okay, so if we look at something like the temporaries, any subroutine can use them, and it should just assume that it can manipulate them and it never needs to save them. So if the caller, before calling the subroutine, if it's got important data in the temporaries, it needs to save them either to other registers or to memory, and so on. This of course links in with the compiler's course, and I'm sure you will go through this sort of ABI in more detail there. Now let's have a look at an example function in assembler. So here I've got an example in the box on the right of an integer function that computes the Fibonacci sequence. So there's a very simple bit of C code, which hopefully makes sense. It's not that far removed from what you might see in Java. And it just goes around a loop performing that calculation. If we actually have a look at the fib code, if I look here, that's a move instruction, and here we're moving A0, so the value n is passed in as an argument register A0 into the temporary. We've then got A0 is then set to 0. We set A1 to be 1, and these correspond to the initialization that we have over here. Then we've got a loop test So we check whether our loop variable that's now in T0, whether we've got to the end or not. So that's the loop test there. And then here's the main body of the loop. And the main body of the loop basically does the equivalent to j minus minus. So j is held in T0. We've got the add, the subtract, and then conditional jump to go around the loop. And at the very end we return here, and the value we've been computing is already in register A0, and that's how it's going to get returned. So that brings us to the end of this lecture, so let's just summarise some key points. So despite RISC processors often being simpler and lower power while offering similar performance, CISC machines, sort of x86 machines from Intel and AMD, continue to dominate the PC space due to requirements for backwards compatibility. I wait to see how this progresses in the next few years, and in particular it looks like Apple is going to start using ARM RISC-based cores even in their desktop machines, and they already use them of course in things like the iPad and the iPhone. RISC dominates the mobile and microcontroller space. RISC-V, this new, relatively new open source instruction set, is clean and simple, complete, open source. We're getting good compiler support, linker support and so on, and there's a growing community. RISC-V is great for teaching and research. It's open, it's relatively simple, it's extensible, and we'll use it extensively for the rest of these lectures and also for the ECAD and architecture labs. And we're also using and extending RISC-V for research in the computer architecture group, and in lecture 10 I will tell you a little bit about the research we're doing there on designing more secure computers. And with that I will finish this lecture. Thank you.